Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will use a Python program that uses the Fortran MKL library on the Fram Linux cluster. After logging into Fram, we access the Login 3 node. For our production jobs using MKL with Python, we'll be using the Work folder. I've created a folder named MKL Python within the Work directory. Inside the MKL Python folder, we have 3 files with the same name but different extensions. First, let's examine the file with the F90 extension. This file includes the initial Fortran subroutine we discussed earlier. Following the initial subroutine, there is another subroutine named MKL, DGEMM. In this subroutine, matrices A and B are inputs, and matrix C is the output. It utilizes the MKL routine DGEMM, which we explained in video 31. Then, we'll look at the Python file. We will use a matrix dimension of 32768 and utilize both Fortran modules. Therefore, we'll apply the Fortran MKL routine for matrix multiplication instead of the NumPy routine used in our last video. Let's examine the job script file with the sh extension. This script is the same as we used in our last video, and it requests 32 cores on a single node. We'll load the matplotlib module, which also loads NumPy and the Fortran to Python command. We're setting OpenMP environment variables. The Fortran module is built using the same Fortran to Python command as demonstrated in our last video, but now we have included the option for loading the Fortran MKL routines. We'll execute the Python program and use script commands to measure the build and execution time. The remainder of the job script is unchanged from our last video. Before submitting the job to the Slurm management system, we clear the terminal. Once submitted, the job is assigned a job ID number. Using the slurmq command with the me option shows that the job has been computing for 17 seconds. After the job completes, we examine the slurm output file using the correct job ID number. The matrix multiplication was executed in approximately 92 seconds, indicating successful parallel computing. The NumPy routine completed the same task in about 88 seconds. This demonstrates that MKL with Python provides similar performance to Python using the NumPy routine. Importantly, this shows that Fortran MKL routines can be used with Python to achieve excellent performance. However, it's advisable to first check if your calculation can be performed with a NumPy routine before considering a Fortran MKL routine. Let's examine the files created in the folder. We notice new files, including copies of the original files used in this computation, with the job ID number appended to their file names. The file with the long name highlighted in green contains executable Fortran modules that the Python program can utilize. This file is generated by the Fortran to Python command. Let's examine the output file generated by the Fortran to Python command. It indicates that 2 Fortran subroutines will be converted into Python modules. The file also provides guidance on how these modules should be used in the Python program. In our Python program, we followed these instructions with the addition of the prefix fort before using the module names. Before submitting the job once more, to obtain a better measurement of the CPU efficiency, we will clear the terminal. First, we'll make some changes to the job script with the Emacs editor. We'll skip the building process of the Fortran module, as it is already built. This approach will provide a clearer indication of CPU efficiency during parallel computing. After submission to the Slurm management system, the job is assigned a job ID number. We see the job has been active for 19 seconds with the SQ command. After the job completes, we notice additional files in the folder. These include new copies of the original files used in the computation, with the job ID number appended to their file names. We can examine the Slurm output file for the last job using the correct job ID number. The matrix multiplication was now completed in approximately 90 seconds. The CPU efficiency was now around 84%. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder Cluster, Work, Support, Parallel, Computing, YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos, and you can copy any of these files to the home folder. In our next video, we will show more details on executing Python production jobs on the Betsy Linux cluster. I am looking forward to the next video, wishing you all happy computing in the meantime.